Hello friends, welcome to the second lecture of chemical energetics. In the first lecture, we have seen statements of first law of thermodynamics. The first law of thermodynamics can be stated in different ways. I am going to just revise that statement. First statement is energy can neither be created nor destroyed, although it may be converted from one form to another form. The second statement is the total energy of an isolated system remains constant, although it may undergo transformation from one form to another form. Third statement is whenever certain quantity of some form of energy disappear and exactly equivalent amount of some other form of energy must be produced. Fourth statement is it is impossible to construct a perpetual, that is, a machine which would produce work continuously without consuming energy. So, these four are the statements of first law of thermodynamics. Now, we are going to study mathematical formulation of the first law of thermodynamics. So, see, suppose we have a system, okay? That system have internal energy, that is U1. Now, if heat Q is supplied to that system, that supplied heat may be used up partially to increase the internal energy. So, initially the internal energy of the system U, then after supplying heat, that internal energy become U2. Okay, that is, initially the internal energy of system is U1, and then after supplying heat, that internal energy become U2, and the partially that heat is used to do some mechanical work, so that U1 minus U2 is the increase in internal energy, and we can denote it may be delta U. So, delta U is equal to Q plus W. Okay. I am going to repeat what we have done initially. We have system. The internal energy of that system initially is U1. When we supply heat Q to that system, that supply heat is used for two purposes. First one is to increase internal energy, so that internal energy become U2 and do some mechanical work, which is denoted W1. W. So that increase in internal energy from U1 to U2, that difference is U2 minus U1. It is shown by delta U, and delta U is equal to Q plus W. So this is equation 1. That equation 1 is the mathematical formulation of the first law of thermodynamics. This equation 1 is the mathematical formulation of the first law of thermodynamics. Okay. So you have to remember that equation, that is delta U is equal to Q plus W. In any examination or in any oral, if examiner asks to you what is the mathematical formulation of the first law of thermodynamics, then you have to say that delta U is equal to Q plus W is the mathematical formulation of the first law of thermodynamics. Now, if the work done is work of expansion, as I have said, there is some work done if that work done is work of expansion, that W is equal to minus P delta V. Now, why W is equal to minus P delta V? This we will see in incoming lectures. But here now that you have to keep in mind that if work is done, if work done is work of expansion, then W is equal to minus P delta V. Now, substitute value of W in equation 1. Then that equation 1 become Q is equal, that equation 1 is become delta U is equal to Q minus P delta V, because W is equal to minus P delta V. Now, rearrange equation for Q. Then we get Q is equal to delta U plus P delta V, and minus P delta V is change sign, that is it become plus P delta V. So Q is equal to delta U plus P delta V. If that work done is work of expansion, now if the changes are very small, if the changes are very small, so that case we have to write dq in place of q. When changes are very small, then we have to write dq in place of q, then du in place of delta u, and p dv in place of p delta v, so that all these are written when the changes are very small. So our equation becomes dq is equal to du plus p delta v. This is equation 4. So this is about the mathematical formulation of the first law of thermodynamics. Okay. Next topic is second law of thermodynamics. First question arises that why the second law of thermodynamics was needed. We know that the we know that the first statement of first law of thermodynamics is the statement is energy can neither be created nor destroyed. It can be converted into one form to another form. But this first law is incomplete because it does not place any restriction on the flow of energy. Hence, the second law of thermodynamics needed. So, why there is the need of second law of thermodynamics? Because first law is incomplete as it does not place any restriction on the flow of energy. So, today we are going to study three different statements of the second law of thermodynamics. The first statement is written by Kelvin. The statement is no process is possible in which the sole result means overall results. No process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. This is the Kelvin's statement of second law of thermodynamics. Now we will see the explanation of this statement with the help of this diagram. See, these are two diagrams, that is A and B. In diagram B, firstly, we have going to consider diagram B. This is a hot source. This round is a heat engine. This round is a heat engine, and this heat engine takes heat from this hot source and convert it into work. So there is a work done. So what diagram B tells us? It tells us that this heat engine takes heat from hot source and all this heat is converted into work. But according to the statement of Kelvin, this cannot be possible. What Kelvin says that no process is possible in which the sole result in the absorption of heat from a reservoir and its complete conversion into work. So, this is not possible. But now, what actually happened? Actually, this heat engine takes heat from the hot source and heat is converted to the work. And some heat is converted and some heat is transferred to the cold sink. So not overall heat is converted to the work, but some is transferred to the cold sink. So this happens actually in reality, and it is explained by Kelvin, that is no process is possible in which sole result is the absorption of heat from reservoir and its complete conversion into work. Reservoirs means hot source. Now we will see the second statement. Second statement by Clausius statement. What he had stated that heat does not flow spontaneously from a cold body to a hotter body. So, what is meant by spontaneously? Spontaneously means a process which can take place without help of any external agency. So, without help of any external agency, heat does not flow from cool body to the hotter body. So, we have know that heat can flow from hot body to cool body. But if you want to reverse it, that is flow from heat from cool body to hot body, it cannot be possible spontaneously or without the help of any external agency. See the diagram. This is a hot sink and this is a cold source. Now we know that heat can flow from this hot sink to the cold source. But if you want to reverse that is flow from heat from the cold source to the hot sink. So this is not possible. So statement is heat does not flow spontaneously from cool body to the hotter body. And spontaneously means the process which can take place without the help of any external agency. So, two other statements are second law of thermodynamics. These two are the statement of second law of thermodynamics. Now, we will see the third statement of second law of thermodynamics. This and that statement is in terms of entropy. Now, what is meant by entropy? This we will study in incoming lectures. Now, at this point, we are going to consider only the statement of second law of thermodynamics. Okay, the statement is the entropy of an isolated system increases in the course of spontaneous change. So, in the earlier slide, we have seen what is meant by spontaneous. Spontaneous is this process takes place without the help of any external agency. So, the flow of heat from hot end to the cold end, it is a spontaneous process. Then, diffusion of gas from high pressure to the low pressure, it is a spontaneous process. And very common example is the flow of water down a hill. We know that water falling from top to the bottom, it is a flow of water down a hill. It is also spontaneous process. So, during that spontaneous changes, the entropy of an isolated system increases. Now, what is meant by entropy? Entropy is the measure of disorder or measure of randomness. Okay. Now, in our incoming lecture, I will discuss in detail what is meant by entropy and what are the characteristics and other things. But at this position, you have to remember the definition of entropy. Entropy is the measure of disorder or measure of randomness, and the statement is the entropy of an isolated system in the course of a spontaneous change. So overall, delta S total is greater than 0. The entropy is shown by sign delta S. The entropy is shown by sign delta S. And S is used for entropy. And delta S, it is the different delta S the entropy is shown by sign S, and that S is used for entropy, and delta S, it is the difference entropy. S final and S final minus S initial, that is entropy final minus entropy initial is the delta S. So that delta S total is greater than 0. So it means that the initial entropy is less than the final entropy. Okay. Initial entropy is less than final entropy. It means that when we go from initial to final state, there is increased entropy. So that difference become greater than 0. So, this is the third statement in terms of entropy of the second law of thermodynamics. So, before studying the further point, now this chapter chemical energetics, these are basic things you should know. In previous, we have seen objective of the thermodynamics, limitation of the thermodynamics, zeroth law of thermodynamics, different statement of first law of thermodynamics, then mathematical formulation of first law of thermodynamics. Now mathematical formulation of first law of thermodynamics and these three statement of thermodynamics. So all these basic things you should know before studying in detail chemical energetics. These are the reference book for this chapter. The reference book is Atkins Physical Chemistry. This is by Peter Atkins, Giulio Di Paola, James Keeler, 11th edition, and this book is published by Oxford University Press. Thank you.